All right, continuing our study of the properties and attributes of functions, we're going to take a look at combinations of functions. So the worksheet that you have defines what those combinations are, either adding, subtracting, multiplying, or dividing two functions together. We're going to look at one particular example here. We'll pick f of x to be x squared and g of x to be our reciprocal function that we just learned about. And we'll take a look at symbolically what these combinations look like, and in a table, and then also in a graph. It turns out that combinations are one of those things that you have to work and force an arrow diagram to work really hard on. It's just not the thing that the arrow diagram representation was built for. So we're not going to try to force it on that. There are places where it is useful if you're doing just the right things, but this is not one of those. So let's take a look at what f plus g of x would look like. Well, it just says it's going to be f of x plus g of x, so this would just be x squared plus 1 over x. Okay, it's a combination of two different parent functions. This is not just some kind of transformation of the functions, not a simple transformation. It can be kind of thought of that way. We could think that we're shifting x squared up by 1 over x. The thing is, it's not being shifted up by the same amount every time. So that has a little bit different effect. F times g would be x squared times 1 over x. Which we can think of, well, that's x squared over x, and I can reduce that to just x, and that's almost true, except for some domain things that we're going to have to look at and talk about here, because this does not exactly look like that, and we'll pop back up here and we'll take a look at that in a little bit, but mostly that would just look like x. F divided by g of x would be x squared divided by 1 over x. We know that that's the same thing as x squared times x over 1, which is x cubed. And again, it's almost going to look like x cubed, but not quite exactly. Might have been interesting to do this as a g of x over f of x, but this is what we got. Okay. All right, so in the table, what does that mean when we're actually putting these things together? We've got values for these things, so this is the f here. It didn't come through real well. But we've just kind of picked some x values here, and we're going to plug them in and see where this goes. So negative 2 squared is 4, 1 squared is 1, negative 1/2 squared is 1/4, 0 squared is 0, 1/2 squared is 1/4, 1 squared is 1, 3 squared is 9. I think I actually meant for that to be a 2. It's probably a 2 on your page, so we'll make that a 4, so all that matches. G is 1 divided by, so this is going to be a negative 1/2. This will be a negative 1. 1 divided by negative 1/2 is actually negative 2. 1 divided by 0 is undefined. We cannot do that. Okay. 1 divided by 1/2 is 2. 1 divided by 1 is 1. 1 divided by 2 is 1/2. So if we're doing f plus g, it's really just as simple as adding these two numbers together. 4 plus negative 1/2 is 3.5. 1 plus negative 1 is 0. 1/4 plus negative 2 is negative 1 3/4. 0 plus undefined, that's undefined. Okay. 1/4 plus 2 is 2 1/4, and 1 plus 1 is 2, and 4 plus 1/2 is 4.5. I'm going to plot this graph over here kind of while we're going here. So for f plus g, Wish I had more colors here, but let's kind of get the graph of x squared. First, we know what that looks like. Our parent function for x squared has, these are the points that would actually fit on there, and I'm just going to try to kind of lightly sketch that in here because we're probably going to end up with a lot of stuff on this graph. The 1 over x, our parent function there, we knew that that was going to hit here and a half and a fourth out here and about a third, and so this is coming out this direction and then up there because we have that vertical asymptote, and somewhere around through these points and like that. So our green function at -2, it should be at 3.5, and the reason is that we've got this gap from up to this point at 4, and we're adding on a -1/2, so that is going to look like that. That's going to go there. At -1, we are at 0. At 1/4, we're at -1 3/4, or not, sorry, not 1/4, but at -1/2, we're at -1 3/4, so that's down here somewhere, not far away from where the reciprocal function was because the quadratic is so close to 0. At 0, it is undefined. Okay, there's a gap in our graph here, and what we notice when we jump to the other side at 1/2, we are at 2 1/4, so we're back up here. So it looks like that vertical asymptote is still playing a role here. 1, 2 is right there, and 2, 4 1/4. Okay, well that's a little bit interesting. It kind of turned around and went back up. So best information that I have, it seems like what's happening on this side is this is just continuing up this way very similarly to what the quadratic was doing, because if I think about what's happening over here, I'm seeing that I'm getting, these numbers are basically 0, and when I'm adding them on, it doesn't change much at all. Okay? The reciprocal function seems to have its biggest impact when we're close to the origin, because we're subtracting these massive numbers away from numbers that were very close to 0 in the first place. So we'll continue to have that there, that vertical asymptote there, and it's still going to have its influence on this side as well, but this is going to dip down here for a little while, and then it looks like the quadratic, as the reciprocal function starts getting closer and closer to 0 again, the quadratic begins to take over, and so we get a graph that looks something like that. Okay. So let's see, I'll try to put another graph over the top of that. Let's take a look at our next one. F times G. We've never seen a graph that looked like that, right? That's fairly interesting. F times G, if we multiply these together, I get a -2 out of that. 1 times -1 is -1. 1/4 times -2 is -1/2. 0 times undefined is undefined. 1/4 times 2 is a half, and 1 times 1, I'll make sure I'm doing these things right. 1 times 1 is 1, 4 times a half is 2. And so if I plot these points at -2, I've got -2, -2. I've got -1, -1. I've got negative 1/2 comma negative 1/2. I've got 0 undefined, can't put anything there. A half comma 1/2 is right there. 1 comma 1, 2 comma 2. If I look at those points, they look like they are falling exactly in a straight line, except for the problem when x is equal to 0. Okay. And if you remember, I said that f times g of x above, or we said, was equal to x. But what happens here is we have a little gap there, and we'll leave an empty circle there because that was not part of the domain of the reciprocal function. And the two of these things working in combination in this way made it look very much like a straight line, and it is so much like a straight line except that for that one point. Okay? And because we couldn't use the 0 in one of the functions at the beginning, we can't use the 0 in the combination of those. All right, I'm going to try to get clever here now, which is usually a dangerous thing. Because what I'd like to do is shift to a different color, but it doesn't look like it's going to let me do that right now. So let me go ahead. Maybe we got it now. Let me pick a color that will show up reasonably well. I'm going to go with an orange. And so division, okay, f divided by g. 4 divided by negative 1/2 is a negative 8. Okay. See if I can also make that a little bit skinnier. Okay. F divided by g. 1 divided by negative 1 is a negative 1. 1/4 divided by negative 2 is a negative 1/8. Okay. 0 divided by undefined, that's still got to be undefined. 1/4 divided by 2 is 1/8. 1 divided by 1 is 1, and 4 divided by 1/2 is 8. So it's going to shoot off on my screen here just a little bit, but we can account for that. So I've got a point at negative 2 comma negative 8. Negative 2, negative 8 is going to be down here somewhere. And then it goes all the way to negative 1, negative 1. It's a point that's been getting used a lot. Negative 1/2 comma negative 1/8. So that's kind of up here somewhere. I've got the undefined point, and then the 1/2 comma 1/8, the 1 comma 1, and the 2 comma 8 up here somewhere. And what that graph is going to look like is it's coming up like this into there, has to skip over that point, but then come out like that. And that is the graph of my cubic function. We studied power functions in the polynomial chapter, and that is what the x cubed looked like, and it's exactly the x cubed except at the origin in this case, because we're not allowed to use that number in the first place. Okay? And that really is our domain considerations. So things that, comments that we can make here are that if a number didn't work in the domain of any of the original functions, then it can't be used in any of the combinations. So the basic idea there is that you've got to look at all of the original functions that may be involved in the combinations, and if they had domain restrictions, things that we couldn't use, then we have to continue to stay with that, even if it looks like they might cancel out. Okay, so that's number one, is that we would have to continue with the domain of restrictions from the original problem, and then we also have to say if the combination, or we'll say this, we'll say check the combination for any new restrictions. So the division, if one of the things is division, it may have introduced something into the denominator that now we can't use. If my original problems were f of x equals x cubed and g of x equals x, then dividing by that x, because we created it that way, we would have to say now we can't use 0 because an x of 0 would have made the g of x equals 0. Range is a much trickier thing. Range on these kinds of things, we are most of the time going to have to look at the graph to see what's going on with the range. Okay. It's lots of interesting things happen, like when we looked at this green function here, the range appears to be all real numbers because of what's going on the left-hand side of that, but there are other strange things that could happen when we start to do combinations. Okay. General message of it, though, is if it says you're adding things together, then that's just adding the outputs of those functions at any particular input. You can work with it that way to make the graph. All right. That is it for a discussion of combinations of functions.